Okay, so today we begin with our last chapter for this course, which is the fields. We will be talking in this chapter about fields and how fields interact in space-time. This is a chapter that is a little delicate, not too difficult, but you should pay extra attention to this chapter because you will see some new notions in physics. So you have to keep up with me on this chapter in order to fully understand it and you understand the physics behind this chapter. Okay, the first thing we have to say is that we are dealing with classical fields, not quantum fields, because quantum fields or the quantum field theory is a more advanced course that you will see afterwards if you are doing theoretical physics. In this course, in this chapter, we will talk about classical fields. And by classical fields, we mean fields with the special theory of relativity in space-time or in this space of 4 dimensions, not quantum fields. So it's not classical in the meaning of Newtonian physics. It's called classical just to make the difference with the quantum field theory that is a more advanced course. Of course, we will be studying the fields in space-time. So as we usually do with relativity, so we have the time and we have the space, the Euclidean space, the dimensions of space. So at least we have a time dimension and a certain number of space dimensions. We always need at least a 1 dimension of time because there is no logic, there is no meaning into considering spaces with no dimension of time or with more than 1 dimension of time. In this universe, in the physics, with the physics we know, with the equations we know, it is practically impossible to have more than 1 dimension of time. So in any space-time where we are studying real physics, we should only have 1 dimension of time, always 1 dimension of time. When you go to space, you can have any number of coordinates of space. So mathematically speaking, you have the possibility to have any number of space or any number of dimensions of space. Because in mathematics, you can make equations on a space-time with maybe 100 or 1,000 dimensions, always having 1 dimension of time and a number n, any real number n of dimensions of space. But in reality, in physics, when we talk about the reality of this universe, when we talk about physics, we know that you need at least and a maximum of 1 dimension of time. So we have this 1 dimension of time always in any system with real particles and real physics. And we need a certain number of dimensions of space. So we can have 1 dimension, particles, or linear dimension. We can have 2 dimension as in a plane. We can have the Euclidean 3D space as we have 3 dimensions of space with the dimension of time. Or we can even go to the string theory with 1 dimension of time and 10 dimensions of space. I will not go into details of string theory. This is another course. So let's talk about just fields. So we will consider a space or a space-time with a dimension t, of course, and a certain number of x's. So x1, x2, x, any number of dimensions of space. So the field in this space or in this space-time is a certain variable. So we are talking about a physical quantity, any physical quantity that is measurable, that depends on time and on space, that we call the field. So the field is just a variable physical quantity that we are observing and measuring in the considered space time. So in any space and time, we are observing and measuring a physical quantity. This physical quantity is called the field. So you don't have to imagine fields like lines of fields, and, as we do in magnetism or as in an electric field. It's not just some vectors that are going from one space to another. Any physical quantity that could be a scalar, not a vector. Any physical quantity is called the field. As an example, you can take the temperature. You know that the temperature vary from place to place and from time to time. Let's talk about the weather. So if you watch your weather every night at the end of the news bulletin, uh, you see that they tell you about the temperatures in different regions of space, and this temperature could vary from time to time. So in the morning you have a lower temperature, at noon you have a higher temperature, etc. So at different places and different times you have a different value of the temperature. So here the temperature is the field that vary from place to place and from time to time. You can also take the example of the velocity of the wind that varies with the position, the time, and also with the direction. Here it's a velocity, it's a vector velocity that has a direction. So in this case, the velocity of the wind, for example, is a vector field, while the temperature is a scalar field. So you always have to see the difference between scalar fields and vector fields. In this chapter, I will be mostly talking about scalar fields. Sometimes I will use vector fields, but especially I will focus on scalar fields. So a field is a measurable quantity, is a physical quantity that is varying with time, of course, and could be varying with space according to how many space dimensions you have in your space time or in your frame. Okay, let's take an example. So if you consider a field phi, which is the letter F in the Greek alphabet. So we will consider a field phi that varies with time and with space, any number of space, 1, 2, or 3, or even 10. So if this phi is a field, let's take a very simple, a classical example as the position of a particle. So let's consider phi as the position of a particle as a function of time and space. So if you draw the variation of phi as a function of time, here I will use, as in classical mechanics, an axis t that is horizontal, not as we usually take it as vertical. So from this time to this time, from the initial time to the final time, phi is varying. So the position of the considered particle is varying with time. So this curve represents what we call the history of the field. So when you see the word history of the field, that means we are talking about the variation of this field as a function of time. So as you see, the position of this particle is varying a long time. So for each value of the time, we have a value of phi, which is the position. So for t equals whatever a certain value, you have a value of phi. For each value of t, you have a value of phi. So you have this curve of variation, which is the history of the field. So how do we describe this history? Of course, the history is described through equations, through physical equations. And the only way to derive these equations is to use the principle of least action. So when you have a real variation in physics, it always follows the principle of least action. So what do we mean by the principle of least actions that you already know is that we are fixing the two endpoints. So the boundaries are fixed. This point is fixed. This point is fixed. And we have a variation between these 2 points, such as this variation represents the least action or the minimum action. So as we saw it earlier, the action is the sum or the integral between the two fixed point, initial time and final time, of a certain quantity that we call the Lagrangian times the differential of time dt. So it is the integral between t initial and t final. If you take a classical particle, let's begin with the example of a classical particle. So L is just the quantity K minus U, which is the kinetic energy minus the potential energy times the differential of time dt. Okay, so you know that the kinetic energy is given as half mv squared, but v squared is by definition the differential of the position with time. And here we are considering phi as the position, as the field taken as the position of the particle. So the kinetic energy is half m d phi over dt, which is the variation of phi, which is the position, the variation of the position as a function of time, which is the velocity. But here we will use the notation of fields. So dx over dt is actually d phi over dt squared. So this is the kinetic energy minus the potential energy u of phi, which is also a function of phi. So this quantity inside the brackets is the Lagrangian L, which is half m d phi over dt squared minus u of phi. This is the classical Lagrangian of particle in terms of the field phi. So field could be the position or any other variable quantity in physics, not necessarily the position. But classically, we always use the position in Newtonian mechanics. Okay, so now we need to find the equations of motion. And the equation of motions are given by the equation of Euler Lagrange that you saw last year in the course of analytical mechanics. So you know about Euler Lagrange. I will not make the derivation of the entire equation of the Euler Lagrange because you already saw it last year. So you have just to remember the course of analytical mechanics of the second year. And you know, I think you know everything about the equations of Euler Lagrange, which is in classical mechanics, it is written as d over dt, dl over d phi dot. Phi dot is d phi over dt. Phi dot is the derivative of phi as a function of time. So here the phi dot is d phi over dt. So it's d over dt, dl over d phi dot. That is equal to dl, or the partial derivative of l over d phi. And if you work out this equation, you will find Newton is a Newton equation, which is m phi double dot, or ma, as you know it from classical mechanics. So this is the acceleration in Newton. So m phi double dot, which is equal to minus d of u over d phi, which represents the force. So if you remember your course of classical mechanics in first year, you know that the force always derives from a potential. You used to write it as F, that is equal to minus grade of U, or minus the gradient of V, or the potential. So the potential, or the gradient of the potential, is the derivative with respect to phi. So the force is minus the gradient of the potential energy. So minus du over d phi, or del u over del phi, as in the classical mechanics. So this is F, which derives from a potential, minus du over d phi, that is equal to ma, or in this notation, it's m phi double dot. So we have a problem. We have to find these equations of motion. So our problem is to find the minimal action. And here, when I say minimal action, I mean the extremal action. So it could be minimum, it could be maximum. So I always use the term minimum because it is easier to understand it as we say a minimal action. So it's like the principle of least action. So in classical mechanics, or in any type of mechanics, we need to keep the boundaries fixed. So as you see in this previous slide, so we have the two endpoints that are fixed, and we have the curve between the 2 points, that is the curve of least action, or minimal energy. So we need to keep the boundaries fixed, and we need to find the curve of the minimal action. So we can divide the curve as it is done here. We can divide the curve into portions of space, or space-time, and the action would be the sum of small actions along the curve. So for each interval of time, here we have an action. So the total action is the integral. So it is the sum of all the actions along the small intervals of time. This is how we calculate the action. So we can divide this curve, and the action would be the sum of quantities, of course, depending on phi at each time, at each instant of time. Let me correct this. So it depends on phi for each instant of time, or for each interval of time. So when you take differential quantities of time, you have a small interval of time. So this action is a function of different values of phi, because here you have different values of phi. For each interval of time, you have a different value of phi. So the sum is a function of different values of phi. The solution, so, would be to find this curve of minimal action. The solution is to calculate the derivatives with respect to phi, which is the equation of Euler Lagrange. that you know about it, that you know about from last week. So this famous equation of Euler Lagrange that gives you the Newton equations in classical mechanics, and we will also use it in space-time. So this is a non-relativistic description. This is a classical description. So when you consider a field phi that is function of t and whatever the number of space coordinates. So this phi depends on time and a certain number of coordinates of space. Let's consider our Euclidean space. So we have 3 dimensions of space and the 1 dimension of time. But we can also use 10D as in string theory. We can use the 2D as in a plane, 1D as for linear particles. We can also have worlds at 0 dimensions of space. We cannot have anything with 0 dimension of time, but we can have worlds with 0 dimension of space. We can have a world without space. That is the 0D space. So let us imagine a field phi in this type of 0D space. So phi, the field phi, will be only depending of time. So phi would be only a function of t. Let's take classical particles, for example, and calculating the actions, the Lagrangian, etc. They all depend on time, and they only depend on time. All these quantities in classical particles, the position, the velocity, the acceleration, or any physical quantity in classical mechanics, this quantity depends only on time. So actually, these particles belong to a theory of field or a theory depending on only time. So we are working in a 0D space because the coordinate phi, let's take the position for example, is a field because it's a variable quantity, is a measurable quantity in a 0D space, the Newtonian case, because the position is given as a function of time. The velocity is given as a function of time. Here, time is not a variable, time is a dimension. When you give the position as a function of time, so the position is the field, is the physical quantity that is given as only the function of time. So in classical mechanics, when you study Newtonian mechanics, you give an equation of the position that is a function of t, just t. So x is a function of t, v is a function of t. The acceleration is also a function of t. So here, t is the dimension, and x, v, and a are the fields. So when you have a field phi that is only a function of time, so it is a space at 0D. So it is a 0-dimensional space because the field only depends on time. So this is a classical, or it is a theory of fields or a theory of a field in a 0D space. So let us generalize this concept into a field that depends not only on time, but on time plus a certain number of space coordinates. So in space-time. So we will consider a field phi that is a function of t and a certain number of x. So we need to find the equations of motion in this case. So when we say an equation of motion, so it is all about the principle of least action. And of course, the equation of Euler Lagrange. So the least action is the action or the principle that will describe the world or the history, as we say it earlier, as we said it earlier, the history of this field phi. So the phi is a field that has a value for each interval of space-time or for each point of space and time. So if you consider your space-time, which is x and t, as we always do it in relativity, we will consider the portion of space-time where we have this variation of phi. Phi could be varying in the entire space. But if phi is just varying in this portion of the space-time, we have a certain type of boundaries. That could be a rectangle, that could be a square, that could be of any random shape, and it could be the entire space-time. So we need boundaries. So it's like when we have the variation of the position between an initial time and a final time. So here we don't have points, we have boundaries. So our field phi is varying within this space-time. So for each point of this space-time, you have a value of phi. So I will draw it in this way. I will make the plane xt such as the plane is perpendicular to your screen. And our boundaries are this rectangle in red. So this rectangle here, the boundaries in space-time, is drawn in red here, is plotted in red. So the zone delimited by the red line that can be of any shape is the boundaries, is the portion of space-time where we have the variation of the field phi. So phi varies within these boundaries of space-time. So for each point here in the plane xt within the red boundaries, we have a value of phi. So I will take phi as the vertical axis. So a value of phi that is given in green. So for each point in space-time, for each interval here in space-time, we have a value of phi that is in green. So instead of having a curve of minimum action, we now have a plane or a surface of least action. It's not a plane, a surface of least action, because for each point you have here in the red square, you have a value of phi that is given in green. So if you sum up all the values of phi, you will draw a surface delimited by these boundaries. So they will form a surface above the plane x and t. And just remember that x here represents the space. So it's x, y, and z, and whatever the number of space coordinates. So it is the principle of least action. So the boundaries should be fixed. So this line here, the red line, the boundaries of space-time are fixed. So it's like a perimeter or a circumference in the plane xt. It's the analogous of the two fixed points in classical space. So now we have space-time, not space. So this red line is the boundaries or is a boundary of this portion of space-time where we have the variation of phi. It's like a perimeter delimiting the variation of phi. So the values of the field are maintained fixed at the boundary. So the value of phi here at the boundary is fixed. So you can say also that this green boundary line is also fixed because it represents the values of phi for each point of the boundary. If the boundary is fixed here, so the values here on this green perimeter are also fixed. It's the analogous of 2 points in classical mechanics. So the values at the boundaries are maintained fixed. The other value of phi here within these boundaries should vary in such a way to finally obtain the surface of least action, which is the real surface of the variation of phi. So it is the surface now of least action, not the curve of least action. So it is the history of the field in space-time. So now we need to find the equations of motion, of course, using Euler Lagrange. But before that, I will go back to this curve. So here we have two fixed points, and between the 2 points, we have a curve of least action. These 2 points are fixed. Now in space-time, we have a portion of space-time with fixed boundaries, and within these boundaries, we calculate the values of phi for each point of space-time in order to get the surface of least action here in green column. Okay? So this is very important to understand the field theory. So I recommend you to repeat this portion of the video several times in order to fully understand. Okay? So the action, as we always do, it's an integral, a sum over the time, which means it is the sum of the values of the field. Here, the values in green. It is the sum of these values in each cell of space-time. So if we divide our space-time into cells, for each cell, we have a value of phi. And the action would be the sum of all these values of phi to form the surface of least action. So it is an integral over the space-time, not an integral over time. So we need to find the new Lagrangian of this integral. We need to find the Lagrangian. So the action is the integral of a Lagrangian L times, it should be dt in Newtonian physics. Now, instead of dt, the differential of time, we need to put the differential of space-time. So the differential of space-time is not only dt, it's dt and dx and dy and dz. So it's the integral of L d4x or dx mu, as we always use the mu summation over mu, and mu goes from 0 to 3, so it's dt, dx, dy, dz. Okay, so in classical mechanics, d4x is reduced to one dimension, so d4x is equivalent to dt. But here in space-time, we have to consider the 4 coordinates, 1 time and 3 space. So L is the Lagrangian of phi. It's like any Lagrangian of phi that depends on phi at first, and of course phi dot. The phi dot here in space-time are the derivatives of phi in space-time. So the derivative with respect to each dimension. So we will get 4 derivatives instead of one derivative according to time. So we have the Lagrangian phi. Phi is depending on phi itself and on its derivatives, phi and phi dot. So L is function of phi, del phi over dt. Now the derivatives are partial derivatives. Del phi over del t, del phi over del x, del phi over del y, del phi over del z. Or you can write it as phi and del phi over del x mu, and mu goes from 0 to 3. Here you have a lot of notations according to different references. Sometimes you see this type of notation, phi with a lower index t. It means it's del phi over del t, and phi with a lower index x is del phi over del x, etc. So you can write it in this way, or in this way, or in this way. You can choose any notations that makes you feel better. It doesn't bother me. Whatever notation you like, you can use. You can use it. Okay, so let us replace the grid of space-time by points. What do I mean by points? I mean that when you make your cell or the cell on your grid, when you make it smaller, smaller, smaller in order to get differential quantities, you are at the limit of having just points, grid points. So the derivatives would become differential quantities, because the space-time considered the portion of space-time considered is very, very small. So we need to have the minimal action. So in order to have this minimal action, just to arrange the writing. Okay, in order to have this minimal action, we should find the differential with respect to phi and make it equal to 0, as in any regular Euler Lagrange equation. Because in the equation of Euler Lagrange, you have, let's take a classical case. You have d over dt del L over del phi dot, that is equal to del L over del phi. You can also write it as d over dt del L over del phi dot minus del L over del phi equals to 0. You can use this form of the Euler Lagrange equation. And of course, here phi dot is the d phi over dt, or the del phi over dt. So this is the classical equation of Euler Lagrange that gives you the Newton equation. Let's calculate the similar equation or an equivalent equation of Euler Lagrange in space-time. So here, instead of having one derivative or one equation, we will have a series of equations, of 4 equations according to our space-time with 4 dimensions. It's the sum over mu. So mu is from 0 to 3. It's the sum over mu of del over del x mu instead of d over dt, of del L over del phi dot. Phi dot is del phi over del x mu, not just del phi over del t. So phi dot is del phi over del x mu, minus, here we cannot change anything, so we keep the del L over del phi, that is equal to 0. So here it's a sum over mu. So you begin by t, it's del over del t, del L over del phi over del t minus del L over del phi, plus x, del over del x, del L over del phi over del X minus del L over del phi, plus the equation along Y, the equation along Z, the entire sum is equal to 0. So it's actually a sum of 4 equations for each mu. So if you have 0 here, you begin by t, which is mu equals 0, t here, and t here. Then you go to x here and x here. Then you go to y here and y here. Then you go to z here and z here, etc. There's a sum of 4 equations. So it's not only one equation of Euler Lagrange, it's a sum of Euler Lagrange equations. Here in this case, we have 4 equations. So it's an equation for each value of mu, while the classical equation is only a one equation as for one value of t, or for a one dimension that is t. This part of physics is called the physics of continuum medium. So I will not go into details of the physics of the physics of continuum medium, but if you see it in a reference, so you know what we are talking about. This part of space-time and this part of physics, we call it the physics of continuum medium. Okay, now we need L. Let's find our Lagrangian L. So let's keep in mind that L is half m d phi over dt squared minus u of phi, so like the classical L. So this is the classical L. It's half m d phi over dt squared minus u of phi. But here, in the classical case, you only have d phi over dt. But in a relativistic case or in space-time, you have four of this quantity: d phi over dt, and d phi over dx, and d phi over dy, and over dz. So our Lagrangian will be half of m. The d phi over dt squared will become del phi over del t squared plus del phi over del x squared plus del phi over del y squared plus del phi over del z squared. So you have to consider the derivative over the 4 dimensions, not only the dimension of time as a Newtonian physics, but we have to consider the entire the 4 dimensions all together: t, x, y, and z. That's why the derivatives are partial derivatives according to each dimension. So here we have 4 dimensions, 1 time, and 3 spaces. Of course, minus u of phi, which is the potential energy. Here, m is just a number, just a scalar. You can reduce it to 1 or to any value. It's just a scalar. Don't think of m as the mass of the particle. M is just a number. Okay, so if you see this Lagrangian is not totally correct, it's not complete, because here, especially for a wave, you cannot make the difference between space and time. They are all the same. So it's not a very adequate Lagrangian. We should, instead of this equation, use a Lagrangian according to what we usually use in space-time when we write the proper time or the proper distance or any invariant quantity in space-time. We use time minus the dimensions of space. So we use the same convention even with the Lagrangian. So our Lagrangian, taking into account the relativity or the mathematics of space-time, which is a non-Euclidean. Just remember, it's not a Euclidean space. We are working in a non-Euclidean space. So for a wave or for any quantity to be able to differentiate between space and time, we need to use the convention of space-time, which is m over 2 del phi over del t squared minus del phi over del x squared over del y squared over del z squared minus u of phi. Here you can add the 1 over c squared in order to arrange the dimensions, and we also need the c squared here not to reduce it to 1, because here c squared is not just a constant, it represents a speed or a velocity. For example, if you consider this wave when propagating in a medium or in a solid or any medium, the velocity of the wave or its speed would not be c. It would be v, that is c over n, whatever the refractive index of the medium is. So here the 1 over c squared could be 1 over v squared as the velocity of the wave in the medium or in the solid or in any medium. So you need to consider the velocity, the real velocity of the wave in the medium. So here c is really the velocity, not just a constant. So it's you need to put it 1 over c squared in vacuum or 1 over v squared in a medium. Okay, we have the Lagrangian. Now we can find our equations of motion, of course, using the series of the 4 equations of Euler Lagrange that you know for now how to put it. So it's the sum of del over del x mu, del L over del phi over del x mu minus del L over del phi, that is equal to 0. I think here we are missing a del here. Del L over del phi over del x mu. We are missing a del here. Okay, so let's take our Lagrangian or the derivative. Okay, the first derivative is with respect to t. So it's del over del t. Okay. 1 over c squared, you keep your 1 over c squared. The derivative with respect to t of del phi over del t squared is 2 del phi, 2 times the second derivative of phi over t, so del squared phi over t. And the 2 and the 1/2, so you can remove the 2 with the 1/2. So you can keep 1 over c squared, del squared phi over del t squared. Here, don't confuse the second derivative with the derivative squared. Here in the Lagrangian, it's the first derivative squared, del phi over del t squared. Here, it's the second derivative, del squared phi over del t squared. They are not the same. Here it's the first derivative squared. Here it's the second derivative, not squared, not anything else. It's just the second derivative. So don't confuse these two quantities. Okay, so we continue the equation. It's now the turn of x. Del over del x of this quantity, so it's minus 2 del over del x of del phi over del x, so it's the second derivative of phi with respect to x, so it's del squared phi over del x squared. The same minus del squared phi over del y squared minus del squared phi over del z squared. Minus the derivative with respect to phi, So we have here the potential energy minus with a minus would become plus del of U over del phi. That is equal to 0. Okay, so this is the equation, the new equation of Euler Lagrange. So let's consider some particular cases. As I told you, m is just a number. You can put a 1, you can put any number here. It's just a scalar quantity that could be 1. Okay, so let's take an example. A wave, for example, any wave, any electromagnetic wave. Let's consider a potential that is 0. So here the U is 0 and the quantity here is 0. So we will be with, and if you take m as 1 or anything, you will have 1 over c squared del squared of phi over del t squared minus del squared over del squared of phi over del x squared minus, etc. That is equal to 0. So if you see this equation, it's the same, exactly the same equation of propagation of electromagnetic waves that you saw in the course of electromagnetism or electromagnetics of last year. It's the same equation. You found it by classical meanings. Now we are derivating, or we are deriving this equation with the real way of doing physics, which is by considering Euler Lagrange equations in space-time, taking into consideration all the equations or the mathematics of space-time and relativity. So you find the same equation of propagation of any electromagnetic waves that you already know this equation from last year. And you know how to really find it using using space-time. Actually, you were able to find it classically because waves are related to Maxwell equations, and Maxwell equations are invariant. So that is why you can find it by classical meanings. Okay, let's take another example, a mechanical example. The example of any spring or any oscillator. The potential is half mu squared phi squared. Let's take a potential that is half mu squared phi squared. It's the same mechanical case of a spring when phi is the position. Phi is the position, and you know that the potential, the elastic potential of a spring is half kx squared. Here k is the mu squared. So classically, in a Newtonian case, the k that you see in a spring, the stiffness of the spring k is actually mu squared in space-time. So you calculate it as half kx squared in Newtonian physics. You saw this in first year in the course of waves and vibration. So it's the equation of any harmonic oscillator. So here, if you have this potential, so you get 1 over c squared del squared of phi over del t squared minus etc. over x squared over y squared over z squared. Del squared of phi minus u of or plus u of phi, the derivative here. You calculate the derivative del u over del phi. So the derivative of this quantity according to phi, it's 2 over 2 mu squared phi. So it's mu squared phi that is equal to 0. So this is the equation of a higher order of a harmonic oscillator. It's the same mechanical harmonic oscillator that you already know. It's an equation of a higher order harmonic oscillator. It's difficult to find this in classical mechanics because you don't use space-time. Here you can see it. When we use space-time, we can find this higher order equation. Okay, I think it's enough for this session. We will continue on the next video.